In this chapter, we're going to work with normal probability distributions. Actually, we're going to first look at a different type of distribution called the uniform distribution. And then we'll move into standard normal, and then we'll look at some other types of normal distributions that are non-standard, but they're still normal distributions. This chapter deals with continuous random variables. Continuous random variables can take on any one of a range of values in an interval, not just a single value, a single discrete number like the discrete variables we studied in the previous chapter. A continuous random variable, if you think of the number line, a continuous random variable can take on any value at all on that number line, not just the whole numbers. The discrete random variables only take on values that are whole numbers, but a continuous random variable can take on any one of a range of variables from an interval. The uniform distribution is a continuous random variable whose values are spread evenly over a range of possibilities. So for example, if we assume that class length is uniformly distributed over a range of possibilities, we can determine the probability that a class will last for at most any given number of minutes. Let's see how that's done. We remember that probability is just like area. And so that means that if we arrange our class meeting times, our possible class meeting time, since our class extends all the way up to 50 minutes, the class meeting time could be anywhere from 0 to 50 minutes. I don't know, maybe there's a fire drill and class gets ended right there. Or maybe the teacher decided to let you out early and so class gets ended right there. So we can't calculate possibilities for each of those individual values because it's a continuous random variable. There's an infinite number of possible values between 0 and 50, and if you wanted to calculate that probability, you wouldn't really have a rectangle. You would just have one straight line going up. There's no area there. So you can't calculate the probability for an individual value of x if x is a continuous random variable. If you could calculate all the possible values for all the random all the values of the random variable between 0 and 50, you would be getting these segments that are going straight up. Eventually they would totally fill in that rectangle, and that rectangle has to have an area equal to 1 because that's what the total probability is. It's 1. So that means if the rectangle is 50 units this way, it must be 0.02 units that way, because 50 times 0.02 is equal to 1. And so that's why the height of this rectangle is 0.02. And that's exactly why I've drawn the picture the way I've drawn it. So you can use this idea to find the probability that your class will last at most 48 minutes, for example. At most 48 minutes means that 48 minutes is the longest time. That means you're thinking of all the probabilities of all the values for the time that class can last between 0 and 48. So that means the segment here is 48 units long. Well, how high is that rectangle? That rectangle is 0.02 units long. And so the probability that the random variable is less than or equal to 48 shouldn't be difficult for you to see that that's the same as the probability that the random variable is less than 48, because remember, this segment right here, straight up, doesn't have any area. So whether you include the 48 or not makes no difference because the area of that segment is equal to 0. So we usually don't have a less than or equal to, we usually just use a less than when we're talking about continuous random variables. So the area of that part of the rectangle that's shaded is 48 times 0.02, which is 0.96, or a 96% probability that the class will be at most 48 minutes long, and that's 48 minutes or less. The probability the class will last between 45 and 48 minutes is easily calculated here because we have a uniform distribution. We have this nice rectangle right here. So we could just calculate the area of that rectangle. We would get 0.02 for the height times 3 for the length, and that's going to give us 0.06, or a 6% probability that the class will last between 45 and 48 minutes. You could also calculate it this way. The probability that x is between 45 and 48 you can find by calculating the probability that the variable is less than 48, which means that you're calculating this area of this rectangle, and then subtract from that the probability that the class will be less than 45, which means you're finding the area of this rectangle and subtracting it. And that leaves you with this rectangle right here. So let's see, what's the probability that x is less than 48? Well, that's just 48 times 0.02, the area of that rectangle. The probability x is less than 45 is just 45 times 0.02, the area of that rectangle. And now we have a common factor of 0.02. Let's factor that out. I'm doing this on purpose because I want you to see that it's exactly the same as this calculation here. So we'd probably do it this way for this problem. But for the class of problems that we have to work in this chapter that deal with the normal curve, we have to calculate our probabilities this way. And here's why. Uniform distribution, the normal curve, is curvy. So there aren't any rectangles in there. There are things that are kind of like rectangles, but they're not rectangles. And what you have to remember is that the horizontal axis extends infinitely that way, and not only that, but the normal curve, these guys, extend infinitely that way and never cross the horizontal axis, and infinitely that way. Remember, these are called the tails. So that's the left tail, and over here is the right tail. So the two tails extend infinitely in both directions. Most of the data is centered or concentrated in the central part. Remember, the empirical rule says most of your data is within 2 standard deviations of the mean. In fact, almost all the data in a normal distribution is within 3 standard deviations of the mean. So the standard normal distribution is just a special normal curve that has a mean of 0 and a standard deviation of 1. Not all normal distributions have mean 0 and standard deviation 1. Some normal distributions have a lot less variance or standard deviation, so they'll be more pointy like that. Other normal distributions are much flatter, and so they look like that. But it's still a normal distribution because it still has that characteristic hump in the center and the two tails that extend left and right, along with the symmetry property. So the first method for finding probabilities or areas by using z-scores is to use table A2 in the back of your text. So just remember that the standard normal distribution has a mean of 0 and a standard deviation of 1. And you actually have two tables back there. You have a negative z-scores table and a positive z-scores table. In the body of the table are cumulative areas that are on the left side of the z-score. So let's look at the table and see what this means. So here's the table, and here's a figure that goes with the table, this figure right here. Notice that in this figure, the shaded region is to the left of the z-score. That means that any area value in the body of this table, all these numbers in the body of the table, all those numbers correspond to z-scores or correspond to z-scores and have these numbers that I circled there are areas to the left of a z-score. So for example, if you wanted to find the probability that z is less than 1.14, less than means to the left of. So you're finding the area to the left of the z-score, 1.14. And so to do that, you go to the table and you look for the z-score 1.14. So the way we do that is we first find 1.1, which is right here in the column here. And then in the row across the top, we find the 0.04. And then we find the intersection of those two, that row and that column, intersect at the number 0.8729. And so that means that the probability that z is less than 1.14 is 0.8729. And that also means that this shaded area here is 0.8729. That area that I've shaded here represents the probability, and it's 0.82, what did I say, 8729. Rounding to 3 significant digits, we get 0.873. And if we want to write that as a percent, we can write 87.3%. So 87.3% of the total area under the normal curve is to the left of the z-score 1.14. Sometimes you have to find the area on the right side of a z-score. The area on the right side of a z-score corresponds to a greater than inequality. So if you want to find the area or the probability that z is greater than a value, that means you're finding the area to the right of 1.14, for example. And so I've shaded that area to show the area to the right of 1.14. Remember, in the previous problem, we calculated the area to the left of 1.14 to be 0.8729. So that means that if you add those two areas together, you should get the total area of 1, because remember, the probability that a continuous random variable equals a specific number is 0. So all you have to do is use the rule of complements. The area to the right of 1.14, which is the probability that z is greater than 1.14, is 1 minus the probability that z is less than 1.14, or 1 minus 0.8729, which is 0.1271. And that's the rule of complements, which you always have to use the rule of complements when you want to find the area to the right side of a z-score. Okay, so in this slide I'm showing you just a negative z-score to the left of the mean, but it doesn't matter that it's a negative z-score to the left of the mean, you're still finding cumulative probabilities from the left. So all the numbers in this table, just like the positive z-scores table, all these numbers represent areas on the left side of a z-score. And so, for example, if you want to find the probability that z is less than negative 0.57, and since that's a less than, we can read that directly from the table. Less than means left cumulative area. And left cumulative areas are exactly what's in the table, areas from the left. So we can look up this number in the table, negative 0.57, which is negative 0.5, and then up here you have the 0.07. And so negative 0.5 plus 0.07, that gives me 0.57. So there's my negative 0.57. And I see that that probability is 0.2843. Well, that's how you find that probability. Now, let's look at a few and see how we can make some sense out of these numbers. So the first example here is, sorry about that, the first example here is the probability that z is greater than 0.54. Well, the probability that z is greater than 0.54 is this shaded region. You can't look that up in the table because this is a greater than, and the table gives you the probability that z is less than 0.54. So to solve this problem, you have to look up the probability that z is less than 0.54 and then subtract that from 1. So this probability is equal to 1 minus the probability that z is less than 0.54. So let's get that answer. The probability that z is less than 0.54, we calculated, I guess we did 0.57, so let's do 0.54. 0.54, here's 0.5. And here's 0.04, so the intersection of those two is going to be 0.7054. And so you have to subtract that from 1. And so when you do 1 minus 0.7054, I'm just doing this quickly on my calculator as I speak, 7054, you get 0.2946. So this probability is 0.2946. You can sort of tell that from the picture. It looks like about 1/3 of the area, about 30%. Now, what about the probability that z is less than negative 0.54? Well, that probability should be the same as the probability that z is greater than 0.54 because of the symmetry of the normal curve. So this would also be 0.2946. The probability that z is greater than negative 0.54 is going to be 1 minus 0.2946. What about the probability that z is less than 0? Well, 0 is the mean of the standard normal distribution, and exactly half of the area is to the left of that mean, and exactly half of the area is to the right of that mean. So the probability that z is less than 0 is 0.5. I will leave it to you to figure out, well, I guess I better not. I'll help you with this part. So the probability that z is between these two numbers, let's see how we can figure that out. We can take the probability that z is less than 1.53. That's going to be the area all the way over there. From this 1.53 is right here. That would be calculating all of that area. But that's not all that we want. We have to subtract this part. That part is the probability that z is less than negative 1.02. So we can find the probability that z is less than 1.53, and we can subtract the probability that z is less than negative 1.02. And when we do that, we'll find the area in between those two numbers, which is what I have shaded in red. So look that number up in the table, and look that number up in the table. The reason I can't do that for you right now is because I've only got the positive table showing here. I don't have the negative z-scores table. So I'll let you do that part on your own. Probably the best and easiest way to find these areas is to learn how to use the TI calculator. And I do have a video showing that on Sophia. So I'll just walk you through the syntax for the commands. So what you have to do is access the distributions on the calculator, and the video on Sophia shows you how to do that. And what you want is the distribution called normal CDF. And be careful that you don't pick the normal PDF. You can see right here there are two normal distributions. One of them has a P and the other one has a C. The C is the one you want because C stands for cumulative. So we're going to find the cumulative area, and the nice thing about the calculator is it doesn't matter whether it's on the left side or the right side of your Z, because you enter the lower bound, which is the number that's on the left side, if it's a number. I'll more about that later. And then the upper bound, and then the mean, and then the standard deviation. If the mean is 0 and the standard deviation is 1, you can leave those off. The calculator assumes that it's 0 and 1 if you leave them off. So if you're using a normal distribution that's a standard normal, you can leave those off. But if it's not a standard normal, has a different mean and a different standard deviation, you have to put the mean and standard deviation in. So let's look at the first example, the probability that z is less than negative 0.54. Well, if you look at this number line that I've drawn, you see where negative 0.54 is, the numbers less than negative 0.54 extend infinitely to the left. So you have to kind of fool the calculator into using a very large negative number for your left bound. And so the way to do that is to use the negative E99. And again, all that does is it tells the calculator that you're going out to negative 10 to the 99th power, which is very, very far out on the left side. So that's the lower bound. The upper bound is the number you're stopping at, which is negative 0.54. The mean is 0 and the standard deviation is 1. So if you enter that into normal CDF, you will get the area value. For greater than, well, the picture here shows you that if you're greater than, you have a lower bound of negative 0.54. And what's the upper bound in this case? Well, it's extending forever. So you enter a very large number. The large number that you enter is E99, which is scientific notation for 10 to the 99th power. That's a pretty big number. So it makes the calculator think that you're extending out forever. So if you enter normal CDF with the lower bound negative 0.54, upper bound of essentially infinity, and then you can leave off mean of 0, standard deviation of 1 if you want. I just put it there for completeness. The final example, the probability z is between two numbers. Now you have a lower bound of negative 1.02. You have an upper bound of 1.53, and you have a standard normal, 0 means, and standard deviation of 1. So there's the syntax. Notice that for this one you have a bounded interval on both sides. You have a left bound and a right bound. And so that's how that one works. I hope this helps you. I would recommend that you use the calculator.